Chapter 11.1 Part 2 Gravitational Fields continued. By the end of this section, you should be able to derive and use the equation G is equal to Gm over R squared. Previously we saw F is equal to Gm1 m2 over R squared. Now over here you have another equation, G is equal to Gm over R squared. We will see how to derive this equation. Okay, then use this equation for the gravitational field strength due to a point mass. See, gravitational field strength, G is the gravitational field strength, also called the acceleration of free fall. Earlier it was a F there. F is equal to Gm1 m2 over R squared. Now we have just G. Use the equation V gravitational is equal to minus Gm over R squared for a radial gravitational field. We will see what this is. Okay, you will learn about gravitational potential. Compare electric and gravitational fields. You will learn three different kinds of fields: electric fields, gravitational fields, and magnetic fields. There are similarities between these fields. If you consider electric fields and magnetic fields, there you also get a force of repulsion. But in the case of gravitational fields, there is no force of repulsion, only attraction. Okay, then here we have a radial field. Now it doesn't matter whether this is a moon or a earth, the field lines are pointing towards it. Why? Because if you have an object, the object is attracted towards it. So these are the gravitational field lines. They are pointing towards the center of this point mass. Okay, that's why it's a radial field. It's like the radius of a circle. It's pointing towards the center. That's why this is called a radial field. But if you consider part of the earth, we are on a small portion of the earth. Over here the gravitational field lines are vertical. So there we have a uniform. We are in a uniform gravitational field. But if you look at the earth from the moon, you will have a radial gravitational field. If you look at this diagram here, you can see the earth and the gravitational field lines are pointing towards the earth. Here this is a radial gravitational field. That is when you look at the earth from outside the earth. But if you are inside the earth, then you can see it's something like this. The gravitational field lines are perpendicular to the surface of the earth and they are parallel to each other, because these field lines will meet at the center of the earth, which is a long distance away. So approximately they are parallel to each other if you consider a small portion of the earth. So here we get a uniform gravitational field. Uniform means the field lines are spaced out equally. Here we have a uniform gravitational field. Here we have a radial gravitational field. Okay, then the gravitational field strength G. We already learned this equation. F is equal to Gm1 m2 over R squared. F is the gravitational force, also called the weight. This capital M is used for the bigger mass. Simple M is used for the smaller mass. For example, if it is the earth and a satellite, capital M is the mass of the earth, simple M is the mass of the satellite, because the satellite is lighter or has a lesser mass than the earth. Now what we will do is, over here, F is equal to mg, because this is the weight force. Weight is equal to mg, W equals mg. So we can write this as mg. Once you write this as mg, the small m and the small m cancels out. Now let's say this is the gravitational force on the moon by the earth. So the mass of this m is the mass of the moon. M and m will cancel out. Then you will get Gm over R squared. That is how you get this equation. Now in the beginning of the lesson you had this. So very simple. This is the derivation. That is, the field strength is dependent on the object being acted upon. You can see the mass of the smaller object is not in the equation. Okay, so again, that is, the field strength is independent of the object being acted upon. What that means is, you can see the m cancelled out. In the example here we talked about the moon and the earth. The mass of the moon is independent of the gravitational field strength. It depends on the mass of the earth in this example. So it is the earth which is exerting the gravitational force on the moon. So the gravitational field strength depends on the earth, not on the moon. That's what it means by this. is independent of the object being acted upon, but it depends on the object that is causing it, causing that force. Okay, so that is about gravitational field strength. Let's go through an example to help you understand this better. Calculate the gravitational field strength caused by the Earth at a distance of a geostationary satellite which orbits at a height h of 35,800 kilometers above the surface of the Earth. The radius of the Earth is RE, E for Earth, R for radius, that is equal to 6,400 kilometers from section 11.1.1. Now we are in 11.1.2. We have the mass of the Earth as 6.02 into 10 to the power 24 kilograms. Distance from the Earth's center. This satellite, a geostationary satellite, is a satellite which always faces the same part of the Earth or the same surface of the Earth. For example, let's say if there was a geostationary satellite located right above us, then it will always face us no matter how much the Earth rotates. It will also have the same period of rotation as the Earth because it has to face the same part of the Earth as it is a geostationary satellite. Okay, so the satellite is at a height h above the surface of the Earth. Now remember the equation here, r is the distance from the center of the Earth to the center of mass of the satellite, center of mass of the Earth to the center of mass of the satellite. So we have to consider the height above the Earth as well as the radius of the Earth. Okay, so that's why we add these two here to get r. This is the radius of the Earth, this is the height above the surface of the Earth that the satellite is located at. We add the two, these all given in the question. 35,800 plus 6,400, then we will get this. Now we can use this equation, G is equal to Gm over r square, to find the gravitational field strength at that height where the geostationary satellite is located. So G is the universal gravitational constant, and it is also called the gravitational constant. Don't confuse the gravitational constant with the gravitational field strength. This is a common mistake students make. G is called the universal gravitational constant or gravitational constant for short. But simple G is the gravitational field strength. It is also called the acceleration of free fall. Okay, so don't confuse gravitational constant capital G with simple G. Then we have r squared. R we already found over here. Then m is the mass of the Earth, because this is the big M. Mass of the Earth. The mass of the satellite we don't consider because it cancels out when you use this equation. Alright, so the small m cancels out, the big M remains. The mass of the Earth is much greater than the mass of the satellite. Then we will get, now this G is also exerted by the Earth. So here when this G is for a certain body, then we have to use the mass of that body. This is the gravitational field by the Earth, this is the mass of the Earth. So this and this has to be, simple G and capital M has to be for the same body. Okay, so we get 0.23 newtons per kilogram or 0.23 meters per second square. Now you have learned that the further and further you move away from the Earth, lesser and lesser will be the gravitational field strength. On the surface of the Earth, it is about 9.8 meters per second square. But see, it has reduced to this much because this satellite is 42,000 or rather we can say 35,800 kilometers away from the surface of the Earth. So at that distance, the gravitational field strength of the Earth has reduced to this much. And if you go an infinite distance away from the surface of the Earth, the gravitational field strength there will be zero. Okay, so the further and further you go away from the Earth, the lesser and lesser will be the gravitational field strength. Now same thing with the moon or any other body. You can see the further and further you go, the distance between the field lines increases. The more concentrated the field, the stronger the field there. Now over here, if you take a certain area, here let's say we have a rectangle, in this rectangle if we draw a rectangle here, it will occupy 3 of these lines, but same rectangle over here occupies only 1 line. So The more field lines in a certain region, the stronger the field in that region. The lesser the field lines, the weaker the field. Yeah. So that's why when you go further and further from a body, for example the earth or the moon, the field becomes weaker. Therefore the gravitational field strength G becomes weaker. And lastly we have gravitational potential. So far you learned about this and how to get this equation. Now we will learn about this. V equals minus Gm over R. V you have seen before for potential difference, you have seen the letter V. So this is also something similar. This is the gravitational potential. So we have this gravitational potential is equal to minus Gm over R. This is the equation that you have to know. So we have this one, and you can see here there is a R squared, but over here there is only just one R. So this is the important equation. Okay, we'll go through this bit because students have some difficulty understanding this gravitational potential. So we'll go through a bit more into detail about this. Potential energy is that possessed by an object by virtue of its position. For example, if you consider an object above the surface of the earth, when you move further and further from the surface of the earth, the gravitational potential energy of the object increases if it's close to the surface of the earth and if you move further from the earth. Okay, surface of the earth. So it depends on the position. Same thing with elastic potential energy. If you have a spring mass system, the more you pull the mass away from the spring, the greater will be the elastic potential energy in the spring. So it depends on the position. The potential at any point in any type of field is the general concept of the amount of energy needed to get to that position in the field for any object affected by the field. Therefore, for a gravitational field, it is expressed as the amount of energy per unit mass. So joules per kilogram, energy per unit mass. As mass is what is affected by the field. Now in the case of gravitational potential energy, you have the formula gravitational potential energy equals mgh. So the greater the mass, the greater the gravitational potential energy. But here we are talking about gravitational potential. So there is a difference. We have gravitational potential energy and gravitational potential. So gravitational potential, the definition of gravitational potential is the amount of work done per unit mass. So it's that energy divided by the mass. That's why we get the unit joules per kilogram for gravitational potential. Okay, so you see the difference between gravitational potential energy and gravitational potential. Gravitational potential energy has the unit joule. Gravitational potential has the unit joules per kilogram because it is that energy divided by the mass. And here is the definition. You have to know these definitions because in the exam papers they can ask you to write it down. The definition of gravitational potential is the amount of work done per unit mass to move an object from an infinite distance to the field, to that point in the field. Now again, if you have an object at an infinite distance that is out of the gravitational field, let's say of the earth, then what will happen? The gravitational field is zero there. If it is at an infinite distance, there is no gravitational field, so no energy there, no gravitational, no energy. So the gravitational potential there will be zero. But when you get closer and closer to the surface of the earth, say from an infinite distance, what will happen is the energy will increase. But we have a negative sign here because now generally what happens is when you move away from the surface of the earth, if it's close to the surface of the earth, gravitational potential energy increases. But also what happens is the G decreases, the gravitational field decreases the further and further you move away from the earth. So this is something that you have to understand. Sometimes students confuse it. So what you have to remember is when you are at an infinite distance, then the gravitational potential energy is zero, or gravitational potential is zero. But when you come towards the earth, it becomes more and more, but more and more negative. That's why we have the negative sign. Okay, so this is the definition. The definition of gravitational potential is the amount of work done per unit mass to move an object from an infinite distance to that point in the field. As gravitational fields are always attractive, objects will gain energy on moving into a point in the field. And so gravitational potential energy is always a negative quantity. So when you're coming from infinity towards the earth, the energy will increase, but we write a negative sign. It becomes more and more negative, but the energy will increase. Why we write the negative sign is to compare it with an object that is moved away from the earth. When the object is moved away from the earth also, the gravitational potential energy increases. Okay, so to compare it with an object that is coming from far away, at an infinite distance, gravitational field is 0, so the gravitational potential is 0. Therefore, when you come towards the earth, the attraction becomes more, and that's why they say, so objects will always gain energy on moving into a point in the field. So gravitational potential is always a negative quantity. Gravitational potential can be calculated at a distance r from mass m from the equation. So this is the equation that you should know. Okay, so far you have learned about 3 equations. F is equal to gm1 m2 over r squared, then g is equal to gm over r squared, and now you learned the gravitational potential. So earlier you had force, then gravitational field strength g, now you have gravitational potential. So you learned 3 quantities. Now to help you understand this better, again by the way, this definition is important. Afterwards you can write it down, because in the exam paper they can ask you to define the gravitational potential. So what you need to do is just write this sentence over here, from here to here. Alright, for consolidation, let's go through this example. Calculate the gravitational potential caused by the earth at a distance of a geostationary satellite which orbits at a height h of 35,800 kilometers above the surface of the earth. The radius of the earth is 6,400 kilometers. Okay, so let's find the distance from the center of mass of the earth to that satellite. So we will have to use the radius of the earth and the height above the surface of the earth, which is 42,200 kilometers. Then we get this in meters. Now use this equation, very easy. Okay, so once you know the equation, it's very easy. G, always it's a constant, 6.67 into 10 to the power minus 11. You don't need to memorize this, it will be given in the data sheet. Then M is the mass of the earth. Again, you don't need to memorize this, it will be given to you. And then R already here given in the question. Substitute, you will get 9.52 megajoules per kilogram. Now remember, we told you before, gravitational potential is the energy divided by the mass. That's why it has the unit joules per kilogram. So the unit of gravitational potential is joules per kilogram. Now do you remember, if you learned the unit of volt, volt is what? Work done divided by charge moved. So V is equal to W over Q. You learned that equation for electric potential. V is equal to W over Q. So volt is joule per coulomb. Here it is gravitational potential. That's why we have joule per kilogram. So there is joule per coulomb. Here it is joule per kilogram. Okay. Later on, I think we have a comparison between the two. Electric potential, see, gravitational potential. Okay, the gravitational field strength tells us how quickly the potential is changing over distance, and the mathematical connection between the two is, now here it's a differentiation, G is equal to minus dV over dx. Those students who are doing mathematics may be able to understand this. So this is gravitational potential here, this is gravitational field strength. Okay, so we have this one, so that is this divided, the change in this divided by this. So it tells us how quickly the potential is changing over distance, and the mathematical connection between the two is this one. Okay, so we get, now this means the change, D is for change. You can also write it with a delta. Again, delta means change. This triangle is a Greek letter delta. It's better if you are familiar with the Greek alphabet. If you search, you can find a lot of videos about the explaining the Greek alphabet. Here we have capital delta. There are 24 letters in the Greek alphabet. You have both capital letters and simple letters. This is capital delta. Over small distances in which g does not change significantly, this can be calculated using the actual distance change. Okay, so we have this. Now again you see this v and x, only thing difference is that instead of d we have delta here. Then multiply both move the delta x to this side, or multiply both sides by delta x, you will get this then. And finally, as the potential was defined per unit mass, remember the unit was joules per kilogram, and over here we had the definition. You have to memorize this definition. Okay, so gravitation is the amount of work done per unit mass to move an object from an infinite distance to the point in the field. Very easy. Okay, then and is already a negative value. The magnitude of the actual gravitational potential energy change for an object of mass m will then be given by E is equal to m times this thing. Now remember, this had the unit joules per kilogram, and if it is energy, you have to multiply it by the mass, because then only you will get the unit joule. Okay, because this is joules per kilogram, so if you multiply by the mass, then you will get the energy. Okay, so that's how you get mgh. Gravitational potential energy is mgh. Okay, so this delta v is the same as g delta x. Then you get mgh. So the magnitude of the actual gravitational potential energy change for an object of mass m will then be given by this, which we have previously used, and they have given you the reference, this one. Gravitation, P for potential, E for energy, so gravitational potential energy equals mgh. Okay, then we have electric and gravitational fields. We are comparing the two. So here we have the force, F is equal to gm1 m2 over r square. This is what we learned in the previous video. Then here we have electric field. You remember Coulomb's force? F is equal to k q1 over q1 q2 over r squared. Coulomb's force. Then field strength. This is again what we learned here, gm over r squared. So this is the gravitational field strength. This is the electric field strength. You had two equations for electric field strength. Okay, so E is equal to F over Q, E is equal to V over D, and then we have this one also. Then finally, electric potential and gravitational potential. Okay, so V is equal to this one we learn, and then this is for electric fields. Gravitational and electric fields compared. Remember the Coulomb law constant. K is equal to 1 over 4 pi epsilon naught, and it is equal to this. Okay. In the case of gravitational fields, we have this constant G. In the case of electric fields, we have the constant K. And here we have mass m1, m2. Here we have charge q1, q2. And in both you have r, the distance between the masses, or the distance between the centers of the charges. Then here mass, here charge. So you can compare it this way. This G is the constant for this. Here the constant is K. Here we have masses. Here we have charges. Okay. The other R is the same. This is the distance between the centers of the masses or centers of the charges. Okay, and one more thing, the gravitational field cannot be shielded. For example, let's say you keep something, now we are in the Earth's gravitational field, no matter whatever you have in between, it cannot shield the object from the gravitational field. Let's say you keep metal or something, so you are on the floor, then you keep a metal, and then you keep some object above the metal. What will happen when you drop that object? The object will fall. So that metal or nothing can prevent the object falling. So that means you can't shield an object from a gravitational field. If the object is shielded from the gravitational field, the object will just float in the air. because it is the gravitational field which causes the object to be attracted. Okay. So but electric fields can be shielded. So if you keep a metal, okay, a metal sheet or something, it can shield on one side the electric field is there, you have the metal sheet. On the other side there is no electric field. So the electric field can be shielded, but gravitational field cannot be shielded. Okay, that's what's explained here. Although the force and field strength of the gravitational and electric fields share the same force, they do differ in some significant ways. Whilst gravitational forces are always attractive, I already said this, electric forces are not, because you have both attraction and repulsion in the case of magnetic and electric fields. As electric charges can be either positive or negative, the electric field can be in either direction, to or from a charge. Always the gravitational field lines are pointing towards the object. But in the case of electric fields and magnetic fields, if it's a north pole or if it's a positive charge, the field lines will be pointing away from it. If it's a negative charge or south pole, the field lines will be pointing towards it. A charged particle can be shielded from an electric field, but a massive particle, that means a particle with a mass, cannot be shielded from a gravitational field. In addition, the electromagnetic force is significantly stronger than the gravitational force. Okay, so this is the last point here, very important. Electromagnetic force is much more stronger than the gravitational force. So here electric and magnetic, that's why we say electromagnetic force. Okay, let's go through an example to help you understand the equation better. At what distance from a proton would its gravitational attraction for an electron be the same as its electric attraction of the electron when held 10 meters away? Comment on the answer. Now the electrostatic force, also called the Coulomb's force, is given by this equation. F is equal to K Q1 Q2 over R squared. Then the gravitational force of attraction is given by F is equal to G M1 M2 over R squared. Now again, this is considering two masses. For two masses, due to their fields, due to their electric or gravitational forces of attraction. Okay, so we can do this here, 10 meters away. So electrostatic force, now this K is a constant. You have already learned that in the previous chapter when you learned this equation. K is also equal to 1 over 4 pi epsilon naught, and this epsilon naught is a constant, and if you substitute that constant into this equation, you will get another constant K which has this value. Okay, then the mass of a proton and the charge of a proton. So here we are using the charge on the proton, which is equal, and this is between a proton and an electron. So this is the charge on the proton, this is the charge on the electron. And 10 meters away, so meter is SI unit, here we have 10, so we get this. Then gravitational force of attraction. Now this should be equal to this value, that is what the question says. The negative sign indicates that this is a force of attraction, because positive charge and negative charge, they attract. Okay, so even without the negative sign we can do this, and just all we need is the magnitude of the force. Okay, so that's why we don't write a negative sign here, because we want the magnitude of the force. Okay, so this is the electrostatic force of attraction between the proton and the electron. Now we will find the gravitational. Now what we are supposed to find is the, now this is, question is saying to find the distance from a proton. At what distance from a proton would its gravitational attraction for an electron be the same as its electric attraction of that electron when held 10 meters away. So that means the force here and the force over here should be the same. We have to equate the two, because we want to find at what distance both forces will be the same size. Okay. Then we use that over here, we have this. Then R squared is equal to G mm over F. You see here F is the same as this F here, then we get this. So now G, mass of proton, mass of electron, you don't need to remember them, they will be given to you. Substitute and then you will get this. So the distance is, and remember here it's R squared, so you need to take the square root to get R. 2.1 into 10 to the power minus 19 meters is the distance R. The distance between the two centers of gravity therefore is smaller than the radius of a proton. So it would be impossible for the electron to get this close. Gravity is an extremely weak force in comparison to other three forces in nature, but it affects all matter not just things that are charged. So what we found is here, this has to be for the electrostatic force to equal the gravitational force, the object has to be this close. So it's closer than the radius of the proton, which is impossible. The two objects can't come close enough so that it's closer than the radius of the, because we are measuring the distance from the centers of the two. So if it's less than, that means it has to go inside the proton, right? Because which can't happen. Okay, so this shows that the gravitational force is much weaker in comparison to the other forces like the electrostatic force. Okay, but it affects all things. Now make sure you answer all these questions. Again, the definitions you have to memorize with understanding. Answer these questions, check the solutions at the back of the book. Since I explained this in detail, you should be able to answer these questions correctly. And if you have any difficulty answering these questions or even the questions in the previous part, just go through this bit, and you can note down the definitions, the equations, you can note them down, and you should be able to do this correctly. Okay, then the last one is the definition. Gravitational potential is the amount of work done per unit mass to move an object from an infinite distance to the point in the field. Now remember, this was already given over here. Okay, so to help you, they have also given it over here. So the definitions are very important. All right, I think that is the end of the gravitational fields lesson. Again, there are more questions here. Once you finish those questions in the other 2 pages, you have to answer all these questions and check your answers at the back of the book or in the CD. You can also find the answers by, if you Google it, you can get the answers to this textbook. Alright, that's the end of gravitational fields.